Awesome! Welcome back. This is the beginning of the Loading and Performance Learning module. It's pretty short, only a few sections. In this section, we'll be talking about the 4 forces impacting an aircraft. We'll be talking about steady flight and when it's not in steady flight, the angle of attack, the 3 axes of an aircraft, and G-force. The 4 forces acting upon an aircraft in straight and level, unaccelerated flight are thrust and drag, lift and weight. Of the 4 forces acting on an aircraft, thrust is the forward force produced by the propeller or rotor. It acts parallel to the longitudinal axis, and it opposes or overcomes the force of drag. Drag is the rearward retarding force caused by the disruption of airflow. Drag opposes thrust and acts rearward parallel to the relative wind. Lift is the dynamic effect of the air acting on the airfoil. It acts perpendicular to the flight path through the center of lift. It is perpendicular to the lateral axis, and it opposes the downward force of weight. Weight is the combined load of the aircraft itself. This includes fuel and payload. Weight pulls the aircraft downward because of the force of gravity. Weight also opposes lift and acts vertically downward through the aircraft's center of gravity. In steady flight, the sum of the opposing forces is always 0. There can be no unbalanced forces in steady, unaccelerated flight. It means the opposing forces are equal to and thereby cancel the effects of each other. In this example, taken out of the Airman Knowledge Testing Supplement that you'll see at the Testing Center and which is freely available, this is the angle of attack, which is the acute angle between the chord line of the airfoil and the direction of the relative wind. An aircraft has 3 axes passing through the center of gravity at 90-degree angles to each other. The first one we'll talk about is the longitudinal axis, which is roll. A roll is controlled by ailerons. One wing tip goes up, the other one down. Pretty easy. The lateral axis controls the pitch. That is to say, the nose of the aircraft goes up or down, and this is controlled by the elevators. The vertical axis allows the yaw movement, in other words, the left and right movement of the aircraft nose, and it's controlled by a rudder. Put each axis together at the same time and you get aircraft attitude. This is the aircraft orientation, each axis relative to the Earth's horizon. Load factor on the wings will be increased anytime an aircraft is subjected to maneuvers other than a straight and level flight. Anytime you execute a turn, you're increasing the load factor on the aircraft. All right, let's break this down. The force of lift during a turn is separated into 2 components, vertical component of lift and horizontal component of lift. The first one, which I think we all know, vertical component of lift, acts vertically and opposite to the weight, or gravity. If you're new to aviation or you don't have a background in physics, the second one here may be new to you, the horizontal component of lift. This acts horizontally towards the center of the turn. This is called centripetal force. It is the force that pulls the aircraft from a straight line path to make a turn. Here's a picture of a Predator drone. The arrows illustrate the components of lift, the vertical component of lift and the horizontal component of lift. Next up are aircraft stalls. An aircraft may stall from the disruption of the smooth airflow over the wings and a rapid decrease in lift. A stall can occur at any pitch, attitude, or airspeed. All right, we talked about load factors a little bit earlier. Let's go into that a little bit deeper. The load factor is measured in G's, an acceleration of gravity. It is the force to which a body is subjected to when it is accelerated. Any force applied to an aircraft to deflect its flight from a straight line produces stress on the structure. An important note about load factors. Load factors become significant to both flight performance and load on a wing structure as the bank of a turn increases beyond approximately 45 degrees. Let's take a look at this chart. This is another chart that comes out of the Airman Knowledge Testing Supplement, which you will see at the Testing Center, and which is, of course, freely available. This chart is made up of two elements: the angle of the bank in degrees and the load factor. Let's take, for example, we look on the right-hand side, and we are making a 60-degree bank. If we follow that line up, it will hit the curve. Once it hits the curve, you move left. In this case, a 60-degree bank will produce a load factor of 2. We will also see the same on the left-hand side of the chart. Find 60 degrees, move to the right, and the load factor is 2.000. Pretty easy. Next up, weight and balance. An aircraft's weight and balance restrictions are established by the manufacturer or the builder of the UA. I think we can all agree that compliance with the manufacturer's weight and balance limits is critical to flight safety. So, before any flight, the remote pilot should verify the aircraft is correctly loaded. Also, consider the consequences of an overweight aircraft if an emergency condition arises. Again, this is very important. Before any flight, consider the consequences of exceeding the manufacturer's recommended weight and balance thresholds. Exceeding these thresholds include shorter endurance, higher battery drain, and less maneuverability control. Here's an example. You have exceeded the weight and balance of a UA. While you're flying with the payload, a flock of birds approaches. We know that if this situation were to occur, it is recommended that you gain altitude as quickly as possible. If you have exceeded the recommended weight and balance in this example, you have impacted the maneuverability and control.